Select the graph of the function that has the given properties. So f is such that 1, f of 2 is equal to 0. Well, that's an easy one. So let's just check and see if we can eliminate any possibilities because the graph has to pass through 2, 0. So that is the case here. That's the case in the second one. That is the case in the third one and the fourth one. So that doesn't eliminate any possibilities, but that's okay. We'll go on to the next one. F prime of 2 has to be equal to 0. So if f prime of 2 is equal to 0, so if the first derivative evaluated at a point is 0, then that means it is a critical number. And critical numbers are places where we either change from increasing to decreasing, or decreasing to increasing, or you stay from one to the other. But something's happening there. That is the case in the first one. We go from decreasing to increasing. So this is a minimum. So that certainly is, we would have a horizontal tangent line there. So that would be a critical number. The second one, this is not a critical number. And the reason is, if you look at the tangent line at any point, the tangent line is non-zero. It's just whatever the slope of this line is. So this is not a critical number. The first derivative at 2 is not equal to 0. So we can go ahead and throw this one out as a possibility. The next one, we go from an interval that's decreasing, and then we stay decreasing, which is fine. That's still considered a critical number because something is happening there. And same for the last one, we're increasing and then increasing again. So we can eliminate the second one, though. The second derivative evaluated at 2 is equal to 0. So if the second derivative evaluated at some number is equal to 0, then what that means is we have an inflection point. And at an inflection point, what happens is we change from an interval that is concave up to concave down. The first graph is entirely concave up, so there's never a change from concave up to concave down. So we can eliminate that as a possibility because we're not seeing that change. However, here we are changing from this interval is concave up, this one's concave down. So we have an inflection point because we change concavity. This interval is concave down and then concave up. And that's fine. It's still changing concavity, so this is still an inflection point. So these three qualify for those two graphs. Next up, when x is less than 2, f is increasing at a decreasing rate. So if I'm increasing at a decreasing rate, then what that means is my curve looks something like this. So it's going up in value, but it's sort of tapering off. Okay, it is technically concave down, but that's not the only way to have a concave down curve. So we're increasing at a decreasing rate. So it's got to look something like this. And then when x is greater than 2, f is increasing at an increasing rate. So the curve on that interval needs to look like this right here. So it's concave up, but again, that's not the only way to be concave up. It's just increasing, but it's getting faster and faster. So going from left to right, our graph has to look something like this. It has to go from an interval like this to an interval like this. The only one that matches up in that respect is this one right here.